Okay, so fourth week, Bitcoin mining summer series. Today, Karim, Helmy, oh my goodness, I need more coffee this morning, and Sam Doctor are going to give us data-driven research perspectives. So Karim, you're going to kick it off today, and then you'll be the first half hour, and Sam will be the second half hour. And so I'm turning it over to you. And you can, I know you have your introduction and everything ready to go. So I'm going to mute and go off video.
Awesome. Hey guys, I'm Karim Helmy. I am going to be presenting today, and I'm going to be talking about miner hardware fingerprinting. So I'll just start with some quick background. I'll talk a little bit about myself, and then a little bit about mining fundamentals, and then we'll kind of dive into it. So I'm on the research team at Galaxy. I used to work at Coinmetrics, and before that I was at Carnegie Mellon. I'm focused on mining and network data, and my Twitter handle is @KarimHelmy. And so yeah, just I mean, like to kind of start about mining. So Bitcoin relies on proof of work, which requires miners to reach consensus. So miners add blocks to the blockchain and order transactions within those blocks. And to do that, they solve these energy intensive computational problems. So it's a double SHA-256. And the first one to solve the problem is rewarded with the right to order the transactions. So elected as a leader for that block, and gets the block reward and all the fees from the transactions that are included in that block. The way that this race works is that they actually test random values, which are called nonces, and they iterate over these, and the block is accepted as a valid Bitcoin block if the header, including the nonce, hashes to below a certain target value, which is set by the difficulty. Now, the difficulty adjusts every 2016 blocks, so about every 2 weeks, in order to allow for the average block time to be 10 minutes. And yeah, the winning value is called a golden nonce. The block with the golden nonce is added to the canonical blockchain, and the miner receives a reward, and those transactions are included as part of the history of the transaction history. So mining is a race. Mining hardware has gotten way better over time, and the main course of improvement has been through better parallelization. So this has allowed new mining rigs to be more efficient, faster, just generally better at hashing than a normal computer would. So the specialized computers that are used for this are called ASICs, and kind of throughout the history of the evolution of mining hardware, it's gone from CPUs, so just your normal processing unit in a computer, to GPUs, which are usually used for like gaming, could also be used for crypto mining, and still are on a lot of altcoins, and then evolving toward ASICs, which are faster and can only be used to mine Bitcoin. So ASICs are optimized just to be fast and just to process these computations very efficiently. They're not designed to be a perfect random number generator. And so the result is that while you would expect all of the nonces that are in the Bitcoin blockchain to look like static over time, they don't. They end up actually having a lot of signal in them. So this is a plot of all the Bitcoin nonces over time. Each of these is a value between 0 and 2 to the 32nd, which is on the y-axis, and just time on the x-axis. Yeah, you can kind of see like the history of Bitcoin effectively in this plot. So you see that in the early days, people mined using CPUs. So CPUs tested values iteratively. So they start at 0, and then they, that doesn't work, they try 1. That doesn't work, they try 2, and so on. So you kind of get this like pattern where there's a lot of points near the bottom and fewer as you go up. that was the dominant strategy with CPUs. And then you kind of go into the GPU era, where you see increasing density, which means that hash rate is increasing very quickly over time, and in spite of difficulty adjustments. And you also see pretty even perfectly distributed static. GPUs are very good at guessing values randomly in an actual like random and consistent fashion. And then you kind of start to see these weird like streaks. Now these streaks, if you line it up with the history of Bitcoin, you actually can tell that they emerged from this one specific type of ASIC. So the wide, or two specific types of ASICs. The wider part of the streak is the Antminer S7. It's a pattern left by one of Bitmain's old flagship models. And the narrower part of the streak is left by the Bitmain Antminer S9 and that family of miners, which is another one of Bitmain's flagship Bitcoin miners. And in fact, S9s are still like pretty widely in use today, and you can see that a little bit in the plot of the network's history. You know, it's faded, but it's still, there's some presence of the streak. And this makes it one of the most like perennial and really longest running machines in the history of the network. So I'll backtrack a little bit to just like some quick algebra. If you kind of assume that a nonce can be any value between 1 and 10, in reality, it's somewhere between 0 to about 4.3 billion. But if we just assume that it's something between 1 and 10, and we assume that there's 1,000 blocks, so that means that there's 1,000 golden nonces, and 40 of them have taken the value of 3. We have one random number generator that doesn't sample the value of 3, and otherwise samples everything perfectly, you know, randomly, uniformly. And every other random number generator samples perfectly, randomly, and uniformly. We can derive the proportion of the hash power that's actually operated by X. So in this case, there's 40 values that are 3. We can just take the probability, divide it out from what we'd expect it to be, which is 100. And that gives us that 60% of the network is running hardware X. So if we apply this, we can actually backtrace the proportion of hash power that's run by Antminer S7s and S9s based on that plot that we saw earlier of the nonces over time. And this is actually adaptive, and it's not a point in time estimate. So we see that actually like it was over 75% of the network hash rate at one point was running the S9. And it's still pretty heavily in use today, although we do see, you know, we see a lot of activity that's kind of price related because S9s are old hardware, so they're, you know, can be marginally efficient. And we see a drop off recently with the drop in hash rate in China. So what now? Kind of to revisit this, we estimated the proportion of S9s and S7s based on these streaks. But you'll see that the streaks have faded, and that's because there's new hardware on the network. So what you will see though is that there's actually like another pattern that's starting to emerge. So if you go kind of toward the bottom right, you'll see that there's a pretty dense area over there. And then as you go up from there, it gets sparser and sparser. What this looks like is that there's a new machine with a different fingerprint that's becoming more dominant. One or more new machines. And this is just a different way to represent that. It's a little bit clearer. You can kind of see that like orange is denser areas, blue is less dense areas with fewer nonces. The streaks are pretty empty. And over time now we're seeing that like by quadrant, the bottom right quadrant is more, then it kind of just fades out in terms of selection. So what's causing this? It could be any number of new machines. It could be well, not any number. It could be one of a few new machines. So there's the, oh God, there's the Antminer S17, the Antminer S19, the WhatsMiner M20S and M21 and M30 and M31 that have all come up since the S9 became, you know, a little bit less of the workhorse of the Bitcoin network. And so this this new patterning, this new distribution could be caused by any one of them. And so our next goal is to kind of like figure out what's causing this and estimate, create a better visualization map of all the hardware across the network. Another way to visualize this, by the way, is just by looking at the bits in the nonce distribution. So it's a 32-bit number. If you take the individual values of each of them, you can kind of split it up, and this gives you like a more granular estimate. And you can kind of see like which bits are impacted by which pieces of hardware. And just kind of detouring again, you can actually do this for other coins as well. So this is Litecoins. If you see those streaks in the middle, that's an ASIC. And there's also another like denser area near the bottom, also likely caused by some sort of FPGA or ASIC. So yeah, like I mentioned, what our next steps are is we have this new workflow. We want to be able to start with mining rigs, run a lot of hashes on them, and then use that to estimate backwards how many of them are on the network. We want to be able to do better bit level analysis, like the variety that I was showing you over here. So there's a lot of noise here and a lot of duplicated variables, which makes it's a high dimensional problem. But if you do principal component analysis, you can kind of potentially narrow that down and represent this using fewer dimensions, just because that works pretty well because a lot of them are highly correlated. Or you can just do like a max variance analysis. So poor man's PCA, where you see which variables are changing the most and you assume that those are the significant ones. There's also some stuff you can do around automated ASIC detection. So this would apply, for example, with Litecoin over here, where you can see when new ASICs are coming online by assessing if entropy has changed. This is a little bit hard and kind of out there, but it's something that you could potentially do, especially if you had access to pool level data. And yeah, altcoins, Litecoin, ETH, any proof of work coin has nonces that you can use to perform hardware fingerprinting on. And most ASICs, like I mentioned earlier, aren't really optimized to select randomly. So this should be pretty generalizable to other platforms as well. Anyway, thanks for listening.
Karim. Thanks, Karim, for that. So tomorrow, I think that a lot of people will have questions on what you just described and the research you've been doing. So we will have Twitter Spaces tomorrow. Next up, I want to invite Sam Doctor to give some background on the research that he's been doing. Hi, Sam.
Hi.
How are you?
I'm good, thanks.
I'm going to mute myself and go off video so you can get started.
Yeah, I'd love to share my screen.
Yep, you can. You have the option to, right?
Okay. Yeah, now I can. So I'm not sure if you guys can see my screen now. Hopefully this is working. Oh, great. So, I think I take a little bit of a different approach to, to data-driven research into mining. Our approach has really been, starting with surveys and trying to put that into context with the data that is available on, public networks. So this was a piece of research that we did about a year ago. Actually collaborated pretty closely with Amanda on doing this, and actually updated last week. So one of the questions that we wanted to answer was, exactly, where is hash rate distributed globally? And so one of the things that we ended up doing was really trying to understand, first off, how much power was on the network and where that is distributed. And so obviously, trying to do this from a top-down basis, you do have to make certain simplifying assumptions. But one of the key things that we did was look at the halving event last year on, I think it was May 11th, to try and understand what was going on, because we saw hash rate really, peak just before that, and then drop significantly over the following week. And with the halving, what happened was the Bitcoin, the block rewards fell by half. And that meant that a lot of older equipment that was still profitable before the halving was no longer profitable because they had a lot fewer Bitcoin being mined, per unit of hash rate. And so we saw that the network hash rate fell from 136 exahashes to about 81 exahashes over the course of a week. And our assumption was that the bulk of that delta would be from the older S9 class of equipment. And so once you take that into account, that gives us a sense of what the mix might be between the S9 class and the S17 class, which was current at the time. And using that information and the power efficiency, we could get a sense of how much power was available on the network just before May 10th. And more than half of that went offline, but that also gave room for hash rate to grow back into that available power. And so we used that to then, based on surveys and talking to about 50 different miners, to get a sense of first of all, where they were located. And so, we spoke with about 60 plus miners. We looked at about 150 mining sites, and figured that we could identify about 4 gigawatts worth of operational capacity, and actually figure out where that was geographically distributed. Now, we took a lot of additional surveys to try and understand, of the 4 gigawatts that we identified, China was about 730 megawatts, which is a relatively small number, but and clearly far less than various estimates of what Chinese overall capacity is. So we went one layer deeper to try and understand, how much of Chinese capacity have we actually identified. And as we spoke with more and more miners, we realized that we basically got data on almost, the majority of US or Canadian or Icelandic miners, but hardly any information on Chinese miners. And sort of working backwards from there, we got a sense that China was actually about 50% of the overall network. So this was actually published on July 14th of last year. And we've seen estimates that are higher than that. But what was really interesting is that the target hash rate that, the peak target hash rate at the end of May was 179 exahashes. And it currently is, the current target hash rate is about 105. The observed hash rate currently is about 90 or 92, which is actually really interesting because with the Chinese ban, our estimates from last year would estimate that, would imply that about half the hash rate would fall off. And that's roughly what we're seeing right now. So that's something that we think is really interesting. And it's a little bit of a validation of our data point 1 year on. The other thing that we wanted to do was get a sense of what the cost curve looks like for Bitcoin mining. And again, based on our conversations with the different miners, we got to the point where we said, about 50% or 55% of the network is at or under 3 cents per kilowatt hour in power price. Now, that's changing right now because of the Chinese ban. We think that the power prices outside of China tend to be somewhat higher. And so we think that this cost curve is going to shift upward a little bit, particularly from the lower end. So I think that the amount of mining capacity we saw that was sub 1 cent, that's really, shifting. There's still some in Iran that's at that level. And there are a few pockets elsewhere where there are renewables and ancillary services that drive the price down. But most of the cost curve is really about, shifting, we think, to between 2 and 4 cents now. So this was something from last year. And maybe I should jump forward a little bit to where things stand today. So, I apologize for the number of slides here, but here's something that we are looking at. So a year ago, when we published our estimates, we thought that we'd be north of about 235 exahashes right now. And that has changed significantly. A week ago, the target hash rate was 142. Now it's about 105. Part of that deviation, we think, is because of the semiconductor constraint that has been affecting, pretty much every industry globally. But then you also see this decline since then, and that is entirely driven by China's mining ban. Over the next year or so, we think that we will probably see some degree of acceleration, but ultimately we've been digging into supply, the supply chain and lead times around substations and transformers and things like that, that would be required to be able to bring hash rate back up. Because a lot of the Chinese equipment may get relocated elsewhere, but most of the power infrastructure is not going to be, up to code in the US or Canada. So some of it might end up in places like Kazakhstan and Russia, but a lot of that equipment, will not really end up finding a new home. And as a result, we expect hash rate to be significantly below our prior estimates for the next couple of years. And ultimately, there will be a catch up. So, basically, when we think about our methodology, we're really thinking about what what happens to the China hash rate. That ultimately goes to zero. Our reasoning behind the fact that Chinese hash rate may not really relocate easily, and this is something we actually published back in March, as some of these bans started coming in, especially the first coal-fired ban in Inner Mongolia, our view was that there were larger issues at play here. The primary concern for China is less the cleanliness of their power and more to do with capital controls, and the fact that Bitcoin mining allows Chinese miners to essentially convert their renminbi into mining equipment that then becomes Bitcoin that is fungible globally. And so if the true underlying cause of this Chinese ban is to prevent any evasion of capital controls, then Chinese equipment that is already in China would find it hard to get relocated outside, because that essentially circumvents the whole concept behind the mining ban. So there would still be the planned expansion globally, but then the Chinese miners are looking to expand globally as well, specifically for rigs that they have ordered but not yet received, and therefore that either don't exist yet or that do exist outside of China. So those are the two components of what we think would be the new hash rate. And sort of moving forward a couple of steps, people generally look at hash rate and wonder, why is it that we think hash rate is going to grow slower looking ahead than it did in the past? I mean, obviously, part of it is usually, the easy answer is usually the law of large numbers. As the base grows, the growth rates start to slow down. But I think the other factor that's really important to notice is that historically, when the ASICs first came out, they were produced on processes that were already well established and actually old. So, as leading edge semiconductor processes get, the capacity gets taken up by people like Apple or NVIDIA or Qualcomm, we had miners coming in and taking in capacity from older process nodes that was being vacated by these semiconductor stalwarts. And I think that's changing. And as that changes, and as players like Bitmain and MicroBT are operating increasingly at the latest process node, they're competing for limited capacity at those nodes, and that means that they probably would find it harder to get access to as many wafer starts as they did previously. Now, having said that, though, we do think that overall there is growing capacity, and as this constraint eases over the next couple of years, we would see them get more access as well. So that's something that we've been looking at as well. And one of the things that we try to focus on is study the semiconductor market to get a sense of how that plays into overall hash rate. And so one of the things we look at is the difference between net hash rate added and gross hash rate. Gross hash rate is both the growth in the network hash rate as well as replacement of older equipment. And so based on that, historically, we get a sense of how many devices were added based on the latest technology that was available for each year. And the next step, I think this is probably where it gets a little bit, maybe mildly speculative, is as we look at hash rate moving forward, how does that change at the semiconductor level? Now, this is somewhat speculative, but for background, by education, I'm a semiconductor engineer. I have spent a lot of my career studying, semiconductors as well as studying semiconductor stocks at JP Morgan from, covering equity research, names. But this is definitely somewhat speculative, but based on discussions I've had with some of my friends who are in the space. And so as you look at power consumption per square millimeter and hash rate per square millimeter going forward, we can get a sense of what the hash rate would be per wafer and the power consumption per wafer. Now, that then allows us to get a sense of, as we model hash rate going forward, how many wafers are implied by that. And so this is something that we think is a critical piece of critical driver of hash rate over the next couple of years. And that is that over the next 2 years or so, there's a significant number of semiconductor wafers that have been ordered already, but we think that shipments will lag those orders meaningfully. Now, the reason for that is because thanks to the China ban, there isn't the ability to plug in all of those future deliveries outside of China. The constraint here is the lack of substations and transformers and step down equipment and the long lead times around that. So, our analysis suggests that either there would be a buildup of inventory somewhere in the supply chain, or potentially there may be a postponement of wafer starts that Bitmain or MicroBT negotiate with Samsung and with TSMC. And so there would be this delta of roughly about 90,000 or so wafers that either do not get produced or get produced but do not get plugged in over the next couple of years. And so 2023 should see a relatively large catch-up trade. Jumping forward a little bit, we get a sense of what we think the chip count and the hash rate would be for different device classes. The reasoning behind this is that we want to keep power consumption per rig at or current drawn per rig at under 15 amps to be able to take advantage of existing infrastructure. And so that sets limitations around both power consumption and therefore the chip count as we move forward over generations. And that drives us to the number of devices that we think get added each year. And that therefore sort of plays into overall hash rate. But one thing that we wanted to do is, does this actually make sense? And so we decided to backtest this against, backtest is probably not the right word, considering that we have a very, very, very small sample size here. But we basically looked at this to see, based on the framework that we just outlined, how much hash rate did we calculate would get added based on, about 70,000 wafers, and based on the die size that we know for the S9 class. And what is really interesting is the back calculations result in the S9 class of devices adding 27 exahashes, which very closely matches with the actual hash rate that was added in 2018. So, that's sort of our approach to use survey data, to use, data that we can find on the semiconductor industry and talking to industry participants to put together an analysis that first foots to the observed history and then use that as a basis to forecast hash rate going forward. And then we use this to then look at, network power consumption and hash rate. And ultimately what that drives us to is a daily Bitcoin flow per petahash, including a forecast looking ahead. And that then translates into Bitcoin per megawatt hour. Now, this is basically a reference based on on different classes of devices. Obviously, if you have a slightly more efficient device or you tune it or overclock it, it does have an impact on Bitcoin per megawatt hour. But this then allows us to get a sense of what we call a reserve. So if you, as a miner, ran 1 petahash between now and the end of 2030, how many Bitcoin should you expect to mine? And how does that break out over the next few years, year by year? And that's what we do over here. So if you ran 1 petahash continuously from the second half of 2021 through 2030, you would expect to mine about 7.3 Bitcoin. And if you did the same thing with 1 megawatt, ran that 24/7 over the next, through the rest of this decade, you would earn 315 Bitcoin. This assumes that we are upgrading devices as we go. So every time new devices come out, you upgrade the equipment. And because of that, the efficiency of mining increases. So as you see per megawatt, the reserve is a little bit more back-end loaded than on a per petahash basis because of the improving efficiency, which basically means you get more petahashes over time for the same megawatt. So that's basically what I wanted to cover. Maybe we should pause there. And Amanda, I don't know if you're planning to have questions or how do you want to do this?
And that was really interesting. Thank you for sharing. So we're not going to take questions today, but we will tomorrow at the Twitter Spaces.
Okay.
And it will allow anyone who wasn't available to watch this morning. We'll try to post the video this afternoon so they can watch and join if they're in different time zones that don't allow for them to participate at 9 a.m. Eastern time. You made some really interesting points. And I was just talking to Chris from CoinShares this whole time as as this is going on some of the research that you've obviously been conducting. So really looking forward to questions tomorrow. Thank you everyone for joining. Thank you both Sam and Karim for providing your information and research. We really appreciate it. And we will see you all hopefully tomorrow at Twitter Spaces at 9 a.m.